All right. So, since we're sitting at time here, let's go ahead and get started with it. As before, what I'm going to do here is I know that there are still some people coming in just a few minutes late and everything else. We are going to go through the beginning of the material. We're going to finish Whiteboard 6-5, and then we'll talk about exam stuff. So for now, let's talk about our material for the day. A lot of this, I know we're talking about stuff like drag and everything else, but that's going to be a little bit later. If you're actually going through the reading, you would have noticed that half of the reading is about drag. Half of the reading is actually just kind of example problems, different places you might see forces showing up. And I would imagine here that this is possibly at least the third time you have seen this slide right here. And it is indeed the aerodynamics of a cow. But our general gist from this thing is if I have some sort of object, and I have a lot of different forces acting on that object, I can sum up all of those forces into one quantity or one vector that I call the net force. And if I take that net force and the components of the net force, I divide it by the mass, I can find the acceleration of my object because all of those forces summed up together. This is incredibly useful because if we're in a scenario that we've got, say, 5 or 6 forces, we don't have to think about what each force is individually trying to do to our object. We can take all the forces, slap them all together, find a net acceleration of the object, and then go back to our old kinematic equations and figure out how that thing is going to move. Incredibly useful. Wonderful thing. We talked about gravity. We talked about a normal force. Last time, we expanded upon that. We talked about tension, which is what you have with a rope or string or chain or something like that. And the general way that tension works is that anywhere the rope is attached is going to be pulling with the tension. So if I have a rope or anything else, if I have anything, do I have a good rope in front of me? Not really. If this is a rope or something else, and if it's attached to both my hands, it's going to be pulling from a tension on this end and pulling with a tension on this end. Both ends are going to be pulled by that same tension. Friction is the one that's a little bit more complicated. Probably one of the most complicated so far because it comes in 2 different flavors. It's either the kinematic, or not kinematic, the kinetic friction, or the static friction. And of course, this kind of relates to the type of equilibrium we may or may not be in, right? Kinetic, generally speaking, means moving friction. Something is already moving and there's a friction acting on that thing. It's a little bit simpler as well because that equation says the kinetic friction is equal to the coefficient of kinetic friction times the normal force of that object. So that one's nice and easy because it's an equal sign. It's always going to be true. It just makes the entire thing a little bit easier. Now, on the other hand, the static friction is a little bit more complicated because the equation that we have is not equals to, rather it's less than or equals to. And the reason being is because static friction is kind of like a reactive force. In the sense that if I have this book right here, and you can just barely see this in the corner, if I push on this thing, if I push on it just a little bit, it doesn't move. If I push on it a little bit more, so now I've got a medium force, it still doesn't move. Think about the different forces acting on this. Normal force, gravitational force. Me pushing is an applied force. Friction pushes back. Friction stops the book from moving. It opposes the motion. But it doesn't just ramp up and shove the book towards me. It opposes motion. It always tries to stop motion. So static friction is only there in a quantity up to what I am pushing it. Right? I am not going to be experiencing any sort of acceleration in this book because static friction is going to be canceling out exactly how much I am pushing. If I push a little bit less, a little bit less. If I push a little bit more, static friction's a little bit more. It is not until I exceed static friction that the book starts to move. So that's why it is less than or equal to. It is up to a certain value, and if you exceed that value, then the object starts moving. So, I want to try a problem here. Let's imagine we have a wooden block of mass 100 kilograms at rest on a rough inclined plane, and a rough inclined plane implies to us that there is indeed friction. That plane is at an angle 20 degrees above horizontal. The coefficient of static friction of wood on the incline is 0.8. That is our mu value. What is the magnitude of the static friction force on the block? And I have already gone so far as to draw out what your free body diagram might look like. Go ahead and use that. So I'm going to say take 3 or 4 minutes. 3 or 4 minutes, come up with a good answer for this one, and then we'll talk about it together. All right, let's start to talk about this one. So what I've got here, implying static friction force. What does that tell us about what the object is doing? Does anybody have any suggestions? Equilibrium. Static friction only applies when the object is not moving, has no velocity. So if we're asked about a static friction force, we're not moving. So if I look at my forces in each direction, let me go ahead and start with the x direction. Let me say F in the x direction should sum up to be equal to 0. Going in the x direction, I have the x component of gravity. That would be an mg sine of theta. Opposing that is my static friction force, F of s. That's it. I have the mass. I have the angle. F of s would just be equal to mg sine of theta is equal, if we plug in our numbers for this thing, it should be sine for this one. But if we plug in those numbers, we should find a total of, whoops, not that one, not the 700, 335.18 newtons. Remember here that if we're talking about the x versus the y component, the y would get the cosine in this case because it is the adjacent side to the angle theta. X component would be the opposite side. So this is all right. This is essentially the shortest way that we could get to this answer. But there might be a flaw in the thinking in this problem. What have I not yet considered? What else could be going on here that maybe I haven't thought about? Does anybody have any suggestions? I haven't actually checked if friction can be that value. That is exactly correct. I don't know that the static friction can actually supply that much force in the first place. What if the whole premise of the problem is in a little bit of, a flawed thinking to assume that it's actually not moving? What if this thing is actually about to start moving? If we think about that, then what we really need to do is we need to expand upon thinking about what is the maximum value that the friction force could be. I'm going to think about this in terms of, so say F of s must be, if we maximize this, F of s max is equal to that static coefficient times the normal force. To find the normal force, we have to think about the y direction. In the y direction, similarly, I expect it to be 0. But going in that direction, I would have my normal force, and I would have gravity pulling me down. Mg sine of theta. That is, my normal force should be equal to mg sine of theta. Plug that in. What would we find here is that the maximum that it could possibly be is actually going to be 736.7. So we're in the clear this time. Static friction could do a lot more work if we needed it to. If somebody was poking at the back of this thing, trying to send it down the block, down the slope a little bit more, friction could provide more force as needed, but only up to 736 newtons. Oh, whoops, yes, thank you. Yeah, everybody pointing that out, yes. This is static friction force. this is static friction force. What we have calculated is the maximum that static friction could be providing. We know the actual static friction is less than that. What we have just calculated is we could have a static friction force up to this value. So all of this stuff in purple is not actually part of the problem per se, right? We assume that they are not just kind of pulling a fast one on us and not giving us a problem where static friction, would need to exceed what the maximum possible value could be. But it is worth checking because some problems will ask us to compare that. Okay, so this is when I said we're going to talk about the exam just a little bit, and I should do this now before I forget. So the exam we have is going to be next Monday. It is going to open at noon on Monday and close at Tuesday at noon. So there's a 24-hour window where you can take it. Once you start it, you will have 2 hours to go through that exam. But since it closes Tuesday at noon, make sure you are not starting that at 11:30 on Tuesday because it will still close at noon. It is 2 hours, assuming you are not butting up against the final time for that window. The exam is going to consist of, I think I said 18 multiple choice questions. Of those multiple choice questions, every single one of those, it's going to have 6 options. Every question is going to have randomized numbers, randomized order, randomized answers, in some of the cases, randomized questions. Like there might be slightly different flavors of the same question. All of these are original questions written by me, right? All of these questions are things that are not coming from the book, not coming from a test bank, not coming from some other book and pretending as if they were original questions. These are all questions that I am writing myself for the purpose that there are not established solutions to these problems online already. Don't try to look. It's a waste of your time. Like, that is not just me trying to say, don't look for the sake of don't look, but it's a waste of your time to try and find the answers to these questions because I'm writing them, right? I might pull inspiration from other problems, but I'm not going to be copying any other problems. I'm writing them myself. So they are all multiple choice with 6 answers each, but it is set up in such a way most of them are going to be numeric solving. The majority of them will be. There might be a handful of conceptual questions or symbolic problems. For the most part here, though, as we're looking at these things, you are never going to be in a circumstance where you're trying to figure out if you rounded in a slightly different place than I did. I do not follow the rules for sig figs. Right? I might put in numbers and everything else, but I will usually be a little bit more accurate and exact in the numbers that I put down there. If you rounded somewhere slightly differently than me, that should be no problem at all. You should only have one clear answer at the end of the problem. If you have gone through this thing and you have solved out some number and you have 230.5, there's only going to be one answer that is either 230 or 231. The other answers are not going to be splitting the difference between those two or anything else. You are not going to be in a position where your slight rounding difference has put you in a really critical position. Maybe 1 or 2 problems have to, depending on the nature of the problems. Just because on a rare occasion, there is something where it is very, very close for some reason. But I don't think so far, I don't think there's anything we're running into with that. That's usually, there's going to be probably the 3rd exam might have 1 or 2 of those, just because of the way it is. Let me think what else here. It is completely open note because I can't stop you, right? I'm fully aware of that. I'm not using Proctorio or anything else. I think I've talked about that earlier in the semester. Proctorio is a nightmare. I'm not trying to use any sort of proctoring things. The way that I am compensating for the fact that we are doing this in an open note online environment where I'm not in the room with you is the fact that all the questions are original, all the questions are randomized. I have the sense here that if you try to talk with friends about what's going on the exam and what questions you're seeing, you're probably just going to waste both of your time. That's the way that I've tried to set this up. It's just not, you've only got a certain amount of time to work on the exam once you've got it. Once you open that exam the first time, you've got 2 hours to go through it. And if you are trying to spend a bunch of time working on those things, you're just going to run into a rough spot. I don't recommend it. If you can look at the problems and think about it a little bit, draw out a picture or solve through it, you should have more than enough time to get through the exam. The general span that I shoot for is that I can finish the exam within 30 minutes. What else am I thinking on here? Yeah, textbook, old problems, all that good stuff. Make sure you're preparing anything that you want to have with you on the exam. Have it. You will need a calculator. If you don't have a calculator or anything else, there are 100 online calculators. It is Monday from 12 till Tuesday at 12 noon, specifically, Oxford time. No, there will be no class or anything else. The way that it is set up currently is that even if, so it's set up in the 24-hour window because there are people all over the world right now. There are different times where it's reasonable. Sometimes, it might be that you're watching this video right now in a relatively noisy spot that might not be super conducive to actually taking an exam. So if you need to be able to find some sort of private space or some quiet time within that 24-hour window, you don't specifically have to have it at one set time. However, it is also set up in such a way that if this is your only 2-hour block that you have available on between Monday and Tuesday, you still got the opportunity to take the exam then. I'm not going to have a lecture going or anything else during that time. It is just that 24 hours is for the exam. As for practice problems and everything else, after we get out of this lecture, I'm going to be publishing a very, 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 very large mastering assignment. And that mastering assignment has every single question from the book, like all of them set up in the mastering format. So every concept question, every homework question, all of those put into one big assignment all together. So you have plenty of problems to look at and practice from. I don't necessarily recommend immediately going into that, though. Depending on how you're feeling about the questions so far, I would recommend some different things. If you are feeling like you are blazing through both the whiteboard and the homework questions, then go ahead and take a look at the new questions. If you understand the whiteboard problems, but maybe some of the homework problems are a little bit more sketchy, then go ahead and look at the homework problems first, and then the new questions. And finally, if you feel like you need a little bit of review on some of these things, start on the whiteboard, go to the homework, go to the new questions. For all of these, though, my general recommendation is to not look at the same problem twice over. Right now, we can go back to our old stuff, but I would not go through the old whiteboard problems more than once. You are going to be presented with brand new problems, right? Problems that have never been answered before because I'm coming up with them for the first time. So to be able to memorize the steps of a certain problem in a whiteboard problem is kind of useless. In fact, I usually think it's a little bit more detrimental because if you're only working the same 6 problems, you're not learning how to solve new problems. You're learning what steps go into solving those 6 problems. I realize there's more than 6 whiteboard problems, but I think the general concept applies here. This class, the skills we're trying to teach you, we're trying to give you a little bit of a sense of what does the universe do on a grand mechanical scale. But the skill that goes with that is how to look at and approach and solve brand new problems. The best way to practice that is to solve brand new problems. Look at the whiteboard problems once, look at the homework problems once, look at the new problems. Each one of those that you do, don't look at it more than once. Take the problem, solve the problem, go on to the next one. Get practice with seeing new things, knowing how to pick it apart, figure out what you need, what you don't need, what you've already got, how all those things tie together, solving the problem. All of those questions are going to be somewhere between the difficulty. There's a distribution on these. So it's going to be somewhere between the difficulty of the whiteboard problems and the homework problems. Just a distribution with all of those. It's going to be a distribution of the content as well. So, each rough quarter of what we have looked at so far has, about equal representation. Some of the things like vectors. Vectors we have been using in everything so far, right? We just use vectors in this one. So you could make an argument that, vectors are getting a ton of representation because they're in everything that we do. And you're not wrong, but when I talk about distributions of questions, I mean, some of the questions are going to be about adding vectors. No context, vectors. How to work with just the vectors. Some of the questions are going to be about forces and free body diagrams and using those vectors. So difficulty kind of comes into play with that one as well. It is my general sense that the earlier chapters are easier questions because they don't have the extra stuff that some of these later ones do. Your force problems might be your harder questions simply because they oftentimes will include the kinematics within. Trying to think if there's anything else that I need to talk about on that one. I think that's it. The only other thing on that one, if you run into any sort of technical issues or anything else, let me know as soon as possible. I know I've chatted with plenty of you over email so far, and I think, hopefully, the general vibe that I give off on that one is that I'm really kind of casual in all of my stuff. Right? So if you run into a technical issue, if you have panicked and spilled coffee all over your laptop right as you were starting to take the exam or something, you don't have to write out a formal email with signatures and everything else to me. Just say, hey, my laptop is fried, and we can talk about it real fast and figure out some sort of solution. So that's just what I prefer. Even if your computer dies or anything else, send me an email over your phone or something else like that. Just find some way to get in contact. Let me know what's up. The sooner you can, the better. Yeah, please don't come to me. Ugh. Except in very, very extenuating circumstances. Please don't come to me 4 days after the exam and say, hey, I missed the exam. What can we do? Because that's just it's not a good scenario. There's not great solutions once we are that far out. Try to let me know as soon as possible. I'm not planning on taking a look at scrap work. I'm estimating here that if we were to look at scrap work, that's somewhere on the order a little less than 4,000 different problems worth of work that I would have to look at. That's a little bit much. I cannot feasibly look through 4,000 different problems worth of work to understand what's going on. I think I've got pretty good information. I can see, when I go into the analytics of it all, I can see exactly what time you opened problems, what time you answered problems, how long you've spent on each problem, all of that information directly from mastering. So I'm not super worried about that one. If we do run into any sort of issue, keep your work on hand. Could be helpful. But, yeah. Are there any other questions on that, though? Can you skip around? Yeah, you should be able to. I'm not going to have this, look at the problem once and be on with it. That kind of goes against my philosophy of dealing with questions and everything else. So you should be able to skip around, answer the questions in any order, any of that good stuff. There is no penalty for a wrong guess either, which feels like something crazy, but I know like the GRE does that, and that just... Or maybe they don't anymore. I think they don't anymore, but they used to, and that just... That's nasty. I really don't like that. Are there other questions, though? Or has that covered all of it? There is no penalty for wrong guesses. Oh, one other thing that I shouldn't forget. In addition to... So there's going to be the very, 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 very big problem set. But I'm also going to have a much smaller problem set that's probably got 5 or 6 questions in it that is going to be just... Sorry, I read a comment and lost my train of thought here. It's going to be exactly how I write the questions. There are going to be 5 or 6 questions that are in the format that I'm going to be presenting them to you. So you can get a sense of what those questions are going to look like. You're not coming into that totally fresh. You'll have seen kind of the format of the questions before we dive into it. How do incorrect guesses not have a penalty? Some exams, not often at the university level, but some of these like graduate exams and everything else will have like a 0.2 or 0.25 point deduction for wrong answers versus leaving it blank is just 0. The difficulty of questions is varied. There's going to be a distribution of difficulties on the questions. For now, we do still have plenty of material to look at today, or more specifically, plenty of example problems to look at today. So let's dive back into those for now. Let's look at this problem. I've got a block of mass m, symbolic problems, slides from rest at the top of a smooth incline of length L and angle theta, and slides to the bottom. So, when we're talking about a smooth incline, what does that imply? No friction, or such little friction that it's not a big deal. Right? Negligible friction is probably the best way to say it, but we might as well say no friction because we're not really going to consider the friction. So, what I want you to do first, please, draw a good picture and a free body diagram of what you see with this thing. Second, find an expression for the final speed of the block when it gets down to the bottom of the incline. I'm going to give you just 3 or 4 minutes to work on this one, and then we'll take a look together and see what you got. Go ahead and get started. All right, let's take a look here. So, I love these symbolic problems, of course, and I imagine most of you already knew that because I encourage working through things symbolically so frequently. Let me go ahead. There is going to be our level ground. Let's turn this thing so it's at some angle or another so that I can actually draw here. We'll have our level slope come off something like this. We will have our block sitting roughly here at the top, as we might see it. What forces are going to be acting on this thing? What do we think? I'm going to draw the trajectory while we're at it. Gravity and normal force, I would agree with those two. Is there anything else, or are we happy with just those two? Because this is the angle that I can actually draw it instead of, I can't draw it to a downward right angle. I would think that's it though. I think gravity, normal force, there's no friction that we know of, right? We said it's a smooth surface, so friction's not a big deal. So I'm going to draw my normal force coming directly off like this. Some of my question comes then, do I want to decide that this thing is going to be tilted axes, or do I want these to be standard, you know, vertical and horizontal? Do we have any suggestions on that one? What do we think? And why? Because when I'm looking at this thing right now, I see one force pointing down, I see one force tilted. So which one really takes the cake on this one? Or is there something else that I'm not drawing on this? L is here, and I would agree with that. L ties into what my final velocity needs to be. Because even if I was given the height of this slope instead of the length of the slope, even in a circumstance like that, what I would still be needing here is the final velocity. And the final velocity is pointing in this direction, right? This is my direction of velocity final. If that's my direction of velocity final, then it makes a lot more sense if I just tilt my axes now and be done with it, rather than trying to split up components and everything else down the line. I split up one force, and in doing so, I make every other quantity a lot easier to consider. So, in doing that, what should we have here? Let's go ahead and draw this thing coming directly off. Something like that. We will label our angle. If that was theta down there, then this is also theta right here. And that is, there's a geometry argument from this that I did in 6-1 that if that, how I got theta right there is a little bit confusing, I'd recommend going back to 6-1 and watching that one more time. I zoom in and go over that in a little bit more thorough detail. So, of the variables that we are given, we know m, we know l, we know theta, we know the initial velocity is 0. We're asked to find what is the final velocity in this case. So, it's not wrong, it's just something that we haven't talked about yet. So, looking at all the pieces that I've got in front of me right now, V final V initial. I've got a little bit of a sense that there's something to do with acceleration wrapped up in my forces here, and I've got a length. If I'm searching out for my final velocity, I've really got two options. I've got a time option, and I've got a length option, right? Both of them require final velocity, initial velocity, acceleration. But looking at this thing right now, which of the two options is probably going to be a little bit more beneficial for me to use right now? I'd agree, probably the distance one, because I have a distance. I know how far this thing is going to travel. It's going to go down the length of the slope. So in that case, the equation that I want to use from kinematics would be Vf squared is equal to V initial squared, which I know to be 0, plus 2 times the acceleration in the x direction times the length that we are going to travel, which is capital L. So there's our final answer. If only we had the acceleration in the x direction to get to it. But this is how I like to solve a lot of these problems. If I know my problem is going to have multiple steps, what I will do is I'll start at my final answer, and then I'll work backwards from there. So here's what our final answer should look like. Now we just need to find acceleration to plug that in. So let's go a step down. Let's say, okay, well, acceleration in the x direction, that is going to come from the forces acting on this block. If I take a look at all of the forces acting in the x direction, I know f of x should be equal to the mass times the acceleration in x. What goes into the x direction? Well, only that. Only the x component of gravity is actually something that I need to worry about here. mg sine of theta. And if I mess this one up again, catch me on that. But I've got ma is equal to mg sine of theta. I can cancel out the m's on either side. And what I find is the acceleration down the slope is equal to g sine of theta, which, if we go back to our old thoughts, remember here, when we talked about kinematics initially, when we talked about stuff going down a slope, then we said, hey, that acceleration is g sine of theta. I said the slope kind of gets in the way. At the time, you just kind of took that one from me and said, okay, well, whatever. Whatever this crazy man is talking about, we'll just believe it for now. But here's kind of the justification. You have been doing normal force and gravitational force. You just haven't quite realized it. But it ties back into our old material like that. Now we have our acceleration. We can go back up to our top equation here, right? We have done our little side quest to find our acceleration. We take this thing, plug it in. Vf squared is equal to 2 times g sine of theta times L. Take a square root of that whole thing, and I'm going to move the L over just so it doesn't look like I've got theta times L. V final should be equal to the square root of 2gl sine of theta. And that's it. If we take a look at our next problem here, the grittier whiteboard problem 6-6. Let's imagine it's a very similar scenario. Still a block of mass m, starting from rest at the top of a slope of length L and angle theta, but this time it's a rough incline. And that rough incline is very important. The rough incline implies to us that there is some sort of friction acting on this thing now, and that friction, or specifically the friction coefficient, is another given variable, mu sub k. So this is going to look pretty similar to last time, at least in the beginning, but there's going to be some additional steps that we need to do to get a complete picture. I'd still recommend the same method that I took last time. I'm going to do that again, but I want you to take a look at this one and draw a new picture. Don't just add details to the old one. Draw a new picture. Treat it as a new problem. Go through these steps, but find what our final speed would be now, given the fact that there is friction involved in the problem. So take another 4 or so minutes. Take a look at this thing. We'll come back together and see what you got. Okay, let's start to take a look at this one. So, again, what I would recommend, please do draw a new picture. Oh no, there we go. Please do draw a new picture. In my case, I'm using this thing and I'm also time constrained, so I'm going to snag this old one real fast. and just make some additions onto it. But I do recommend getting the practice of drawing a new picture and figuring out what goes into that new picture. For now, let me copy this thing, move it down a little bit. Our big difference is that now, instead of just having these two forces, we are adding to it a friction force. And my first question is, what direction should my friction force point? Not even just on this problem. What direction should my friction force always point? Opposite of the motion, or of the motion that the object wants to make. So in this case, I know that my block wants to start from the top and slide down and to the right, so I'm expecting that my friction force should be exactly opposed to that, up and to the left. Something like this. We know that the block is moving, so it should be a kinetic friction, right? And I assume, again, they can't kind of get like a little tiny bump just to get it started, you know, just enough to overcome that static friction, but not to actually contribute to the velocity. So just like last time, we have a lot of the same variables given to us. We know the mass, we know the angle, we know the initial velocity was 0, we know the length of the slope. Now we also know that there is a certain grittiness to the surface. So I like to draw like a little, almost like sandpaper kind of just to remind myself that there's a bit of grittiness to what's going on whatever my surface has. That just helps remind me. So the problem got a little bit more confusing. There's a little bit more complication to it, but let's go ahead and try and take a look at this just in the same way as last time. Let's start from our final answer and work backwards. We're asked to find the final velocity. Our situation where we're looking for a final velocity, we have an initial, we have a length traveled, and we could maybe find acceleration from our forces, that's still true. I'm still going to stick with that one. V final squared is equal to V initial squared. Cross the thing out because it's 0, but I want to make sure it's there just so I'm complete. Plus 2 times the acceleration in the x direction times L. Same deal as last time. I don't know what that acceleration is. So we need to go to our x forces to figure out if we can find it from there. Now, my x forces are a little bit more complicated. I've got m times a of x. That's all fine and dandy. We still have our mg sine of theta. But now, we also have kinetic friction. So let me start with this. Let me go ahead and plug in. I know that kinetic friction is always the same equation. It's always an equal to. It's never. It's not the same complicated case as static friction. So it's mg sine of theta minus mu k times the normal force. Okay. We are looking for this acceleration. We can't find this acceleration until we find the normal force. So let's do the same approach as last time. Let's work backwards. Where's the normal force going to show up? Well, let me go to my picture. I see the normal force showing up in the y-axis. So let me go ahead and draw out my y forces. I know, let me tilt my head and look at this thing. Even better yet, let's tilt the picture so we can take a look at it like this. I don't expect my block to suddenly start flying up. That doesn't make any sense to me. I don't expect to fall through my slope. That doesn't make any sense to me either. I expect it to essentially stay still from my y-axis and move over in the x-axis. So that means I expect there to be 0 acceleration, 0 net force in the y direction. F of y should be equal to 0. What goes into that? Well, I have my normal force pushing up. I have the y component of gravity pulling down. Cosine of theta, before I mess that up again. But I know that together they should sum to be 0 because I'm not going off of the slope, I'm not going into the slope. I'm staying on the slope, I'm just sliding down it. So between those two things, that's all I've got here. We're looking for f of n. So let's solve out for it. We say that the normal force is equal to mg cosine of theta. We go back up. right? Inception style. We go back, we have influenced everything we need to on this level, we go back up to the next level. What do we see? Plug in what we have just found for the normal force. M A of x is equal to mg sine of theta minus mu k mg cosine of theta. Okay, remember, we're after a of x. So what I'm going to do is I'm going to simplify this out a little bit. I am going to cross out my m's. I don't need all of those. And I'm going to make this look just a little bit prettier before I have to plug it into the next step. I'm going to say g times sine of theta minus mu k cosine of theta. Just pull the g out so it's a little bit less writing. I have my acceleration. Go back up. Now, if I have acceleration, I already had L, I have everything I need to find my final velocity. Final velocity squared is equal to 2 times g sine of theta minus mu cosine of theta times L. Final step, take a square root of this thing. I'm going to move the L over in the same way again, just because I like it to be close by. I'll put the sine and the cosine at the end. That is just my preference in writing, though. It doesn't mean anything for solving. Sine of theta minus mu cosine of theta, all under a square root. And that's my final expression. All right. So, let's keep going on for now. We have had our grittier 6-6. Let's go ahead and look at this one. It's a really good one to look at. Because let's think about this. So I've got a 1 kilogram wood block pressed against a vertical wooden wall by a 12 Newton force. So I want you to first start by drawing a free body diagram, but we run into a little bit of an issue. I've got a question for everyone. What direction does friction point? What do we think? Looking at this thing right now, without solving anything, what direction is friction going? Are we confident that it's going up? How do we know? But there's an applied force. There's an applied force that is also pushing up. So when we're drawing out this free body diagram, I would argue that looking at this thing right now, I think there's a lot of confidence right now that it's supposed to be pointing up, but I wouldn't necessarily say that I know that for certain. Instead, I'm stuck in a difficult position because I don't know necessarily what direction this block wants to move. Because if it wants to move up already, friction would oppose that and point down. If it wants to move down, then friction would oppose that and move up. It always opposes the motion that the block wants to go in. So we're going to split this into two separate pieces. The first part is determining and proving, I should say, because I think a lot of people have their answer already, but I want you to prove to me why you think the friction goes that way. You have to think about where the block wants to move, and then friction will oppose that. The question going back on that, then, is, okay, say you have determined what direction friction should be pointing. Will it start moving? Is there enough force acting on the block to overcome static friction or not? So, take the first 2 or 3 minutes here. See if you can come up with an answer as to what direction it should be pointing. After that, I'm going to say we're going to look at it together. Let's confirm what direction we've got, and then moving from there, we will solve the rest of this to determine what direction it should be moving at the end of it with friction being involved. And we'll take another 2 or 3 minutes after that. So first, 2 or 3 minutes here, figure out what direction it should be going, then we'll chat. All right, so let's first determine what direction this thing should be pointing so that we can approach the rest of the problem. I'm going to draw this thing out. course, a good drawing is always the first step to a good solving. Here's my wall, right? I asked for that to be in black, please. Here's my wall. I've got my block up against it, something like this, right? I've got a variety of different forces acting on it, but one of the unique ones in this case is what we call an applied force, going something like this. So maybe this is like my hand pushing up against it or something else like that. I will typically write an applied force something like this. And it's coming off at an angle 30 degrees above the horizontal. But that's not the only force acting on this thing. What else do I know right now? Not even counting friction. What other forces am I expected to see here? Gravity. Fantastic first choice. But a normal force is the other one that I am expecting. And normal force is a little bit different than we're used to seeing here. What direction does my normal force point in this case? It points to the right. Normal force is not just about opposing gravity. Normal force, remember, is any time I have two objects pressed up against each other. Right now, the box is pushed up against the wall. Since the box is pushed up against the wall pushes back. There is a normal force from the wall on the box pointing directly, perpendicularly from the surface of the wall. What we call normal from the wall. So these are the three forces that I'm expecting, and let me go ahead and draw my axes, my standard axes as we've got on this one. So this has not yet considered friction, and I know that there's a little bit of grit to my wall. I'm just going to call this mu for now because whether it's kinetic or static, I'm going to get to in a little bit here. What I need to think about is what direction does the box want to move? Whether or not friction is going to allow it to move, what direction would it want to move if there were no friction? So let's go ahead and look at this. I'm going to say, okay, well, it's not going into the wall. It's not coming off of the wall. I'm not thinking about the x direction. I am interested in what's going on in the y direction, though. I don't know if there is going to be an acceleration or not, so I'm just going to write out ma for now. If a is 0, fine, no harm done. If a isn't 0, though, we've made sure to capture that. I have the y component of my applied force. In this case, that is sine of 30 degrees, pointing upwards in the y direction. I have mg pulling me down. If I plug in these numbers, I know that the applied force is 12 newtons. Whoa, not theta. Sorry, my thoughts are getting ahead of me here. I know my theta is 30 degrees as I need that thing. I know the mass is 1 kilogram as I need that. I can plug all of these things in, and what I should end up with is 6 minus 9.8. That is a total of negative 3.8 newtons downwards. That is my net force in the y direction, assuming no friction. Without friction. That is, the box wants to move down. If the box wants to move down, friction has something to say about that. That is the direction that friction should be pointing. Now, approach the rest of this, figure out, is the box actually going to end up moving, or is static friction going to hold it in place? Take the next 2 or 3 minutes, take this picture as we've got it, figure that out. Mu of s, if you are interested, is 0.5. Take a look at that, though. Next 2 or 3 minutes. Okay, I do want to start to take a look at this one. I know we haven't had a ton of time to look at this, but we do have a couple other things to look at here. So all of this stuff was kind of done in a bubble. And that bubble is without friction. Without friction, we had these quantities. Now, with friction, we need to think about this. Right, we've got our cereal box now with friction. Now with friction, let's think about what changes. I'm trying to figure out, is there going to be an acceleration in the y direction? Because it could have been last time that we could have seen that the applied force and the gravitational force exactly canceled each other out. And if they had exactly canceled each other out, then we wouldn't have any static friction at all, right? Remember that static friction is a kind of a reactive force. It's only there in as much quantity as it needs to be to try and stop motion. So what we're going to do is we're going to try and see, is there going to be any motion if friction was there? We're going to write this out as F applied sine of 30 minus mg. We've still got these two, but now we're going to add to it a static friction. And the question is, can this be 0? Let me do an equal sign. Let me do an equal sign first of all. Let me do an equal sign with a little mystery above it. Can this equal 0? Is that possible? I've got a couple questions here. First of all, what is the quantity of static friction that this would demand? If we were to entertain this idea that my net force is 0, what would static friction need to be to make that happen? Second, we need to ask, what is the maximum force that static friction could actually provide? Is it capable of providing that quantity that we require of it? So let me start with this. While we're here, while we're already writing on this thing, let's go ahead and solve out what would static friction need to be. And that is, static friction would just need to be mg minus F applied sine of 30. As it turns out, we've already got this quantity, right? We had solved it out before. F applied sine of 30 minus mg is negative 3.8. So we know that the static friction force just needs to be 3.8 newtons to stop this from moving. To stop sliding. That's all it needs to be. Now the question is, can static friction actually provide this, or is it going to start moving anyways? So what we do then is we say, okay, I'll do this as an orange color. Can static friction provide that? Can static friction actually provide that is going to come from our equation F of S is less than or equal to mu times the normal force. And we are going to say, enough of this less than stuff. We're going straight to equals to. This is now the maximum friction force that we might be able to see. What I need to do then is I need to figure out, what is that normal force going to be? What is normal force? So I'm going to go to my x direction, and I'm going to say, okay, well, I know this is not going into the wall. I know it's not coming out of the wall. Let me look at this thing. F applied has some x component. The normal force is also pointing in the x direction. That's it. Those are the only two forces I need to worry about. F of x better be 0. If f of x is supposed to be 0, there is a normal force pushing out. There is the x component of the applied force pushing in. That means the normal force must be equal to the F applied cosine of 30. We take that quantity, we plug it into our maximum possible static friction force, and what we should find for that value is something like, where did I take it? Like 5.17 newtons. 5.17 newtons versus the 3.8 that we required. Static friction can stop it. That is our final answer here. The difference between the two forces is not enough to overcome static friction. As for what's going on in orange, we're basically saying, hey, we need 3.8 newtons from static friction to make sure that we can stop this thing. Then we go over to the orange section, we ask, can static friction actually do that? What is the maximum amount that static friction could provide. We find that the maximum amount that static friction could provide is 5.17 newtons, which is greater than the 3.8 that we had asked of it. Static friction can overcome that difference of forces pushing on the block. But we set it equal to rather than less than or equal to because we are asking for the maximum. What is the upper limit of friction force that could be there? For now, though, I do want to keep moving because I've got one other problem that's pretty important here. That's a fun one to do. And we still got plenty of time, so this is doing all right. For now, let me get back to that comment in a minute here. Sam takes off from rest down a 50-meter high, 10-degree slope on his jet-powered skis, right? Kind of like what we've got in the picture here. It's a little handheld air turbine. The jets on his skis have a thrust of 200 newtons, and Sam's mass is 75 kilograms. If Sam's speed at the bottom of the hill is 40 meters per second, that is our final velocity, what is the coefficient of kinetic friction between his skis and the snow? I'm going to say we're going to take 5 or 6 minutes to work on this one. And then we'll take a look together. Start with a picture. Please start with a picture. I expect to see 4 different forces on that free body diagram. But work on it for a little bit, and then let's compare pictures at the end. Okay, let's start to take a look here. So, as always, the first step is a fantastic picture. Let's see, this should be, well, let me do it up here. Let's make sure we've got enough space for this one. Whoops, I don't want that, I want that, nope. There we go. Gotta have my hands on the right buttons first. So let's go ahead, let's draw out our flat line first. Make sure we've got all that good stuff, and we'll draw something like, let me tilt this just a little bit, something like this, so it's mostly a flat line. That's right around the actual amount of angle that we've got, and here is our good friend Sam. Right? Blocks are so much easier to talk about. So let me think about all the forces that are going to be acting on him. Right? We know that there is, of course, a normal force from the slope. That is not unexpected. All of our usual stuff in that one. But what else do we have here? Gravity, I would agree with that. And I'm going to try and draw this at a downwards angle. I might have to redraw that one. We'll see. What else? Thrust, indeed. A thrust sending us forward like that, and one last one. So I'll say F of t for that. I'll say F of n for the normal force. And a friction pulling us backwards. Gravity doesn't look terrible, actually. That could be worse. So I'll say friction, and we know it's a kinetic friction because we know we're moving, right? And we also have F of g pointing down here. My axes. This is a perfect case. There's not really a question whether I should tilt my axes or not. 3 of my forces are in the tilted axes. 1 of them is not. I'm going to go with the 3. Save myself all the effort. Here's my theta. Got an M. That means this right here is also a theta. Just so we've got all of that information on hand. Let's think about the things that we're given now. We know the thrust is 200 newtons. We know the mass is 75 kilograms. We know that when we start, we had no velocity, but when we ended, what did we have, 40? 40, which is going along pretty fast. We know that there is a slight grittiness to the snow, not much, but a little bit. So I'm trying to draw like a little bit of grittiness just like that. There is some coefficient of friction associated with that, but that is what we are asked to find. What other variable do we have on here that I have not written out yet? H. So I've got a question. We've got H, sure, but if we're thinking about our problems from last time, it was really nice when we had the length of the slope, wasn't it? what if, let's pretend, if we didn't have h, if instead we had some variable, call it s, that's the length of the slope as we go down, wouldn't this problem be so much easier to solve? I would think so. Then we could take an approach like last time. Let's do that. Let's just wave our hand a little bit and say, what if it was s? What changes? Well, in that case, s times sine of theta should give me h. This is just one big triangle, right? So s might as well be a variable that I've already got. Plug it in like that. Not a big deal at all. Now we have the slope length rather than just the height. And we know that it's 50 meters high. So now what I'm going to do, I'm tasked with finding what is that coefficient of friction. So the approach that I'm thinking that we'll take here is I see that friction is pointing in the x direction. Let me start with the x direction. Force in the x direction is equal to, it's certainly not 0, we are accelerating down this hill, max. Must be equal to, I've got the thrust pushing me down, I have the x component of gravity, taken away from that is friction. So then, with all three of these together, I can say, all right, well, I have thrust, I have m, I have theta. I don't know the normal force. That's one tricky thing. I also don't know the acceleration. Yikes. So I could see where my final answer is going to come out of this, but before I can do that, or even better yet, let me solve out for it real fast. If I were to rearrange this thing, I could just right off the bat say that mu k is equal, let's go ahead and start this, let's do this in a couple steps. Mu k times the normal force is equal to the thrust plus mg sine of theta minus m times a. If we divide by the normal force, our final answer, once we get it, is just this right here. So again, if we find this, we have our final answer. This is our final answer. We just need the couple last pieces to plug into it to make this thing work. So let me do that. Let me start with my acceleration. My acceleration is in the x direction. I've already used my x forces, right? I'm not getting an acceleration from the forces, but I do have information on the velocities and the distance that the thing is going to travel. So let me look at the kinematics. Same deal as last time. I don't know anything about the time, but I do know some things about the length. So what I can say is that v final squared is equal to v initial squared, cross that out because it's 0, plus 2 a of x times s. I know the final velocity. I'm after a of x. Let me solve out for it. A of x is equal to the final velocity squared divided by 2 times s. Bam! We have s. Now we do at least. We have the final velocity. We have that acceleration. We can make that a number. And I know I talk about doing symbolic solving all the time, but I might as well. Right? We could just plug that in for a number and find that thing right now. And I'm trying to think if I have that written down already. I don't know that I do. I don't think I actually have that number written down. Let's go ahead and solve it out real fast, though. Right? Why not? Just to check that we've got this thing. If we had 40, so that's going to be 40 squared divided by 2, and then we're going to divide that by s. I'm expecting something like, what, 2.78 meters per second squared? I can just find that number. It's not really convenient to do a whole bunch of plugging in with things, so I want to just have that right there. And remember, the s is the length of the slope. So now I'm going to do the same thing but with the normal force. The normal force, I look at my picture, I say, hey, that shows up in the y direction. So let's solve out for the normal force. F of y must be 0. Not flying off the slope, not flying into it, is equal to the normal force minus the y component of gravity. F of n, in this case, does indeed equal mg cosine of theta. Remember, not always true, but often is. Mg cosine of theta, same deal. I can find a number for that thing if I would like to at this point. The important part is that I have found both of these quantities, these last two pieces, for my final answer. I take that back up to my final answer, and I actually plug in those numbers. When we actually go plugging in all of the numbers, we should find that our final answer is 0.1647. Almost 0.17. So the whole title of this presentation in the first place is supposed to be things about drag, right? What is drag? It's, in a sense, friction from air, but that's maybe not quite all that it is. Aerodynamics drag is generally the force on an object that is moving through a fluid. So a fluid, remember, is any liquid or gas, so atmospheric air, water, methane, whatever fluid you could come up with, an object trying to move through that, or the fluid moving against the object, is going to create some sort of drag. Drag has two big pieces to it. First, pressure drag, which doesn't always show up that intensely, but if anybody has ever watched like a space shuttle re-enter the atmosphere or anything else like that, and you see it kind of like has all of that burning right on the front as it's falling, right? And the whole idea behind that is that it's falling fast enough that the air in front of it is getting compressed and is increasing the pressure by a whole lot, makes it really hot, and that increase in pressure is a force pushing back against the object. The other part of that is known as viscous drag, and in the case of viscous drag, it's the fact that the air particles are like physically moving around the object. That creates some opposing force as well. But drag acts very similar to what we're talking about with standard friction, right? Drag is generally going to be opposing whatever motion the object wants to be going through. But the difference with standard friction is that drag requires some sort of velocity to actually occur. Without a velocity, there's not like a static drag, right? Not in the same way. But there is a simple model, talk about that in a minute, a simple model which looks something like this. The drag force is equal to 1/2 capital C rho A V squared. And that P looking thing is actually a Greek letter rho, R-H-O. Where A is the cross-sectional area, C is the drag coefficient of the object, which is specific to the object. That's a value you'll be given. And rho is the fluid density, which is another value that you're going to be given. Cross-sectional area might be the most difficult part of this thing. Imagine here for a second, if we're looking at this mug, and if you look at this thing straight on, how does it appear to you right now? Think about how you see this thing. Ignoring the handle, what do you see? Any guesses? A rectangle. Exactly. If I turn it like this, now what do you see? If I can actually angle it right, I'm trying to do this on the camera. A circle. Exactly. It depends on how you're looking at it, how it's moving. So for example, if the mug were falling like this, the cross-sectional area would be this circle. But if it was falling like this, then I know you see this differently, but the air sees it traveling as now a rectangle. That's what we mean by the cross-sectional area. It is essentially a two-dimensional slice, right? Imagine any of those old game shows where they need to, like, the people have to orient themselves so that the screen can pass through and not knock them into the water, right? That shows up in a number of different game shows, I think. It's kind of like that, though, right? If something just went through a wall, what shape would it leave? That's cross-sectional area. So this is a little bit complicated, though, because let's look at this thing. 1/2 C rho A V squared. And when we say normal-sized objects moving at slow speeds, we mean most things on Earth. Not planets or anything else like that. Anything from planes to baseballs to anything like that, and I would argue slow speeds is like less than the speed of sound. What goes into that? Well, the simplest case that we might imagine. The simplest case that we might imagine here is let's take a ball and let's drop it. What happens then? Well, the force is acting on that ball. I've got drag pulling up. I've got gravity pulling down. That is equal to my mass times acceleration of the ball. The problem with that is that I have a velocity inside of my acceleration terms. That is, if you recognize this, this is a second order differential equation. Now, realistically, this class does not require you to have already finished Calculus 1. Differential equations are what is often known as Calculus 4. We're not doing this. I want you to see it just to understand why it's a complicated problem. The second derivative of position depends on the first derivative of position, and that's a mess to deal with. And this is, again, the simplest case. You have to imagine if this thing had any x component to it, all bets off. It's a nightmare. Most of the time, this is a plug it into a computer, see what result you get kind of problem. But I do want to bring this up because now you know. Why don't we consider it? Because for the most part, it does make a small adjustment. If we were to consider air resistance, we would have more accurate answers. But the amount of complication added to our problems just to get that little extra bit of precision, it's not worth it. It's simply not worth it. But there is one case that is a little bit easier to solve. Why is there a d squared? That is the second derivative. That's the symbol that we use for a second derivative of y. That is this. Second derivative. Which is different from the first derivative squared. They are different things. So there's a lot of complications that go into that, but there is one specific case of this that is much easier to solve, and that is the case when we have reached a terminal speed or a terminal velocity, as you might know it. Terminal velocity is essentially when you are going so fast that the drag force exactly cancels out the gravitational force. So our acceleration goes to 0, and the velocity that we are at just is essentially taking those two forces equal to each other and solving out for velocity. So, because we don't quite have time to work through this thing, I do want to just show you this example. Let's imagine the scenario. We've got a commercial jet, has a 3.8 diameter fuselage, that's the body of the plane, and a loaded mass of 85,000 kilograms. The drag on the airplane is primarily due to the fuselage, and with aerodynamic shaping, namely that little nose cone right there, this jet has a drag coefficient of 0.37. That is C. How much total thrust must the jet's engines provide for it to cruise at a constant 230 meters per second, assuming the air density is 1 kilogram per cubic meter? So, there are a few different forces acting on airplanes, right? Of course, they are giant metal birds floating through the sky. How do we make that work? Well, there's a few details. We don't need to worry about all of those details. What we're going to do here is we're going to assume that we have some mostly cylindrical looking thing. So we've got that, and we've got something like this, right? Look at that. It's an airplane, of course, right? We've seen these things in the air before. But anyways, we're given a few different variables here. First of all, we have not needed to talk about this too much, but I hate diameters. Ugh. I never like to use them. If I see a diameter of 3.8 meters, I'm going to say, no, that is a radius of 1.9 meters. Because we never use diameter for things, we always use radius. So it always makes more sense for me. If I see diameter, I just immediately convert it into a radius. We also have a mass of 85,000 kilograms. What else do we have here? We have a constant velocity of 230 meters per second. We have a drag coefficient of 0.37. We have a density fluid density of 1 kilogram per cubic meter. And I think that's about it. We are asked to find what thrust do we have to find to make this thing actually go, to stay at what it's doing right now. So realistically, if we were to think about this, there is gravity pulling down on the plane. There is a lift force acting on the plane. Those are things that we're not talking about right now. Instead, I'm focused on the forward propulsion from the engines, the thrust, and the backwards pull of the drag. Like that. Those are the only two I'm going to focus on right now. I'm not going to worry about the Y direction because it doesn't have any implications here. So, with all of this, this looks really complicated, but really, all we need to do, we need to say, hey, we're cruising at a constant speed. Constant speed means the net acceleration is 0. What goes into that? Well, we have a thrust force taking us forward, drag force pulling us back. We know that drag should be equal to 1/2 C rho A V squared. Yikes, so many things that go into that. But that's all right. Looking at this thing, since it's equal to 0, we know the thrust is equal to 1/2 C rho A V squared. I've got a question. If I have a plane, is it flying forward or is it flying side to side? We kind of already know what direction this thing should be taking, right? If I have any sort of plane or anything else and we can make some sort of plane, it goes like this, right? It doesn't just like fly away from the side like that. That's not what happens. Not without a lot of different maneuvering and some other jets going on with these things. So my cross-sectional area is the circle. It's a big cylinder. This is what the cross-section looks like. Area A, if it's a circle, that is pi r squared. If we want a number for that thing, that number would be 11.34 square meters. 11.34 square meters. We have A, we have V, we have rho, we have C, we have everything we could possibly need. Crank it all into a calculator. What we should find at the very end here is the thrust would have to be 111,000 newtons to keep this thing propagating forward. But I think if we're all set with that, that's all I've got for the day. Thanks for being here, team. I appreciate it.